In most coding interviews that involve binary search, you'll be asked to explore and optimize it. Let's explore a naive solution and then discuss how we can do just that. Let's say we have an array that consists of zeros and ones, and that you're guaranteed all zeros appear before all ones. For example, arrays like 00111, 111, and 0000 are valid, while 10 or 0101 are not valid. In this problem, we want to find the first index of the array that is a 1. If no elements are 1s, then we return a -1. A naive solution will look like this in Python. The worst case runtime of this algorithm is O of n, since in the worst case, we'll have n-1 zeros and 1 1. And then we'd have to scan the entire array. Now let's think through how we can speed up this search using binary search. We can start with 2 pointers called low and high, which represent the lowest and highest number that a possible answer could be. In this case, since the answer is always an index, we can set low to be 0 and high to be the length of the array -1 initially. For this problem, we'll start off by letting the loop invariant be array of low to be 0 and array of high to be 1. This may not be the case initially, but we'll explicitly check these cases first. For example, if array of 0 is 1, then that means the answer is just 0, since 0 is the first index where 1 appears. If array of n-1 is 0, then the answer is -1, since there are no 1s in the array. We'll try to halve our search space every single time, and we'll take the midpoint between low and high, and depending whether the value of the array at that index is 0 or 1, then we can update either low or high to be the midpoint. It's easy to see why we set low to be mid when array of mid is 0. That is, we want to ensure that the loop invariant is true. Now for our stopping condition. Notice that low plus 1 is less than high. The reason we did this is that when low plus 1 is high, then low and high are adjacent indices in the array. Once we have that, then we immediately see that high is the first index that is a 1 because it has a 0 immediately before it. Another way to think about this is that we're trying to find the inflection point when the array switches from 0 to 1 rather than finding the first one. To compute the time complexity for a solution, we note that at each iteration we have the distance between low and high. So this is O of log n. Binary search can only be applied if there's only one point where a condition switches from false to true or vice versa. In our example, the condition is array is equal to 1. In other problems, this condition can be different, but as long as the underlying array has some structure where some prefix is all false and suffix is all true, or vice versa, then binary search can be applied. Here's another example you can study. Given a sorted array, we're finding the index of the first element that is greater than or equal to x, and we can return -1 if there's no such element. And finally, note that binary search works on data structures beyond arrays. To demonstrate this, let's compute the square root of a non-negative number. Here's the code. We're using loop invariants similarly to what we did above. Here, we've changed the stopping condition to take into account precision. We also know that the answer will be between low and high, so at the end, we can approximate it as being low plus high divided by 2. The runtime of this is O of log x over precision. I hope this helped paint a picture of different ways binary search can show up in your interviews.